All right, let's talk about something that's literally all around us, but most of us never even see it. We're diving into real-time operating systems, or RTOS for short. These are the powerful, invisible brains behind so many devices we depend on. Systems where getting the timing perfect isn't just a nice-to-have, it's absolutely everything.
So, to kick things off, I've got a question for you. What in the world do your car's airbags, a Mars rover exploring another planet, and a high-tech missile have in common? Well, the answer is timing. And I don't just mean being fast. I mean being flawlessly, predictably, on-the-dot precise. In these systems, a right answer that's a millisecond too late is a wrong answer, and that can be catastrophic. This is the exact problem an RTOS is built to solve.
So here's how we're going to break this all down. First, we'll talk about why it's all about time. Then we'll get into defining what these systems actually are. We'll look at the different flavors, hard, soft, and firm. After that, we'll see how they juggle all these digital events, explore the art of scheduling, and finally, we'll see where RTOS fits into your world.
Okay, let's dive right in. To really get what real-time is all about, we've got to make sure we're all speaking the same language. So let's start with the most basic piece of the puzzle. What exactly do we mean by a system?
You know, at its heart, a system is just a bunch of parts all working together for a reason. The easiest way to think about it is like a black box, right? You put some stuff in, those are the inputs, maybe a sensor reading or you pushing a button, and you get some stuff out, the outputs, like a motor turning on or a light blinking. Simple enough.
Now here's where it gets really interesting. A real-time system takes that whole input-output idea and adds a ticking clock. For these systems, it is not enough to just get the right answer. The system is only considered correct if it produces the right answer at the exact right time. A correct output that's even a little bit late, that's a total failure, period.
And the metric we use to track this is called response time. It's simply how long it takes to get from the input to the output. So that leads to the big question. How fast is fast enough? Well, it turns out that completely depends on the stakes.
And that is the perfect lead-in to the different categories of real-time systems. See, not all deadlines are created equal. The consequences for being late can range from a tiny glitch to a complete disaster. This is where we start talking about hard, soft, and firm real-time systems.
On one end of the spectrum, you have hard real-time systems. Think about a car's airbag deploying. If it misses its deadline by even a fraction of a second, catastrophe. There is absolutely zero margin for error. But on the other end, you've got soft real-time systems. Here, missing a deadline is not ideal for sure. It might make your video game stutter, but the whole system doesn't crash and burn. Performance gets worse, but it survives. And sitting right there in the middle, we find firm real-time systems. These guys have a little wiggle room. Missing one or two deadlines might be okay. But there's a limit. If you miss too many, the system will still fail. It's like having a very strict budget for how many times you're allowed to be late.
And you know, looking at these examples really makes the difference crystal clear. A missile launch? That's hard real-time. You miss the window, you miss the target. Game over. A robot spraying for weeds? That's firm. If it misses a few spots, some crops get damaged, which is bad, but it's not the end of the world. And your console hockey game? Totally soft. A little lag is just annoying, it doesn't break the game.
Okay, so we get the what. But now for the how. How do these systems actually pull this off? Let's pop the hood and look at the engine room. It all comes down to how they juggle something called digital events. This is where the action starts. In the world of an RTOS, an event is like the starting pistol for a task. It's anything that happens that makes the system stop what it's doing and pay attention to something new. It's often triggered by what's called an interrupt. Think of it like a doorbell ringing. You have to pause whatever you're doing to go answer it. A sensor value changing, that's the doorbell.
And these events come in a few different flavors. You've got your periodic events, the ones that happen like clockwork, on a totally predictable schedule. Then you have aperiodic events, which are completely unpredictable, like a person clicking a button. And finally, there are sporadic events, which are rare and unpredictable, like an emergency alarm going off. A good RTOS has to be ready for all of them, all the time. So the whole goal of managing all these events is to build what engineers call a deterministic system. It's a fancy term for something very simple, being completely predictable. It means that no matter what's happening, you can know with 100% certainty what the system is going to do next. And in a high-stakes world, that kind of predictability is everything.
But to get that kind of rock-solid predictability, the system needs a manager, a conductor for the orchestra.
With all these different tasks screaming for attention, how does an RTOS keep everything from turning into chaos? Well, the secret is in the art of scheduling.
One of the most common ways to do this is called round-robin scheduling. Picture a chef who's making 3 different dishes at once. They can't just focus on one, so they give a little attention to the first dish, then move to the second, then the third, and then circle back around. That's round-robin. Each task gets a little slice of time to run. If it's not finished, its progress is saved, it goes to the back of the line, and the next task gets a turn. It's a super fair way to make sure nothing gets left behind.
But hold on. Before an engineer can even pick a schedule, they have to answer a huge question. Is it even possible to meet all our deadlines? To figure that out, they calculate something called the CPU utilization factor. It's basically just a number that tells you how busy the processor is. It answers the question, have we bitten off more than we can chew?
Let's make this real with a quick example. Think about all the things an elevator controller has to do. Talk to the dispatcher, check its own position, register button presses, and so on. Each of those tasks takes a certain amount of time to run. That's the execution time. And it has to run at a certain frequency. That's the period. These 2 numbers are the key.
So you do the math for each task, you add it all up, and what do you get for our elevator? Just 31%. In the RTOS world, that's amazing. It means the processor isn't even breaking a sweat. It has tons of extra capacity to handle everything it needs to do, and then some. It's a very, very safe design.
So we've gone through all the theory, all the nitty-gritty details, but why does any of this really matter to you? Let's connect it all back to the world we live in. This is the payoff.
And we have to start with our hero example, the Mars rover. This thing is the absolute pinnacle of RTOS engineering. It's a completely autonomous robot, millions and millions of miles away from the nearest help. It has to drive, do science, and phone home, all with 0 margin for error. A missed deadline for the rover could literally be the end of a billion-dollar mission.
But what's truly mind-blowing is that you don't need to look to another planet to find an RTOS. They are everywhere. They're in the flight control systems on airplanes. They're in the anti-lock brakes and airbags in your car. They're in life-saving medical equipment, and even in your microwave and washing machine. You're interacting with these perfectly timed systems constantly, without even knowing it.
And that really brings us to the core idea here. The story of real-time systems is completely intertwined with the story of computers themselves. As computers got more powerful and moved out of big data centers and into our physical world, the need for them to react to that world instantly and reliably grew right along with them.
So I'll leave you with a final thought to chew on. Now that you know these systems are all around you, what's the one system in your life that you'd be most worried about if its timing was off by just 1 single second? Your car's brakes? A pacemaker? It's a wild question, and it really makes you appreciate these invisible brains that keep our world running perfectly on time. Thanks for watching.